Swayam Prabha. Digital India. Educated India.
Hello, so welcome to Astrochemistry. This is lecture 14 and this is also tutorial 4. So wherein in the last tutorial, we had started discussing about the astronomical unit system, and I had just started explaining to you about the need for the astronomical unit system, and I just said that for time, it is going to be, for time, the standard unit is a day, which is 86,400 seconds, okay? So this is it, and I'll also clarify, in the last tutorial I had lost track as to whether this was question 3 or 4, right? This is question 4 actually, okay? The first question being the ideal gas equation, the second question being the liquid water availability on Earth versus, like the ISM, the third one being the question on the phase diagram. So this was the fourth question that we started with, okay? So this is the astronomical unit system for time. Now what about for mass? Okay, for mass, the solar mass is taken to be the standard reference. And is referred to as m naught. Now this is page 1. So the currently accepted value for the solar mass turns out to be m naught is something like approximately 1.98 times 10 to the power 30 kilograms. Is this a fixed number? Of course not. It keeps varying, right? Because of a lot of fusion, fission, and around any star, which the sun is also, of course, one. So around any star, you'll have the disk, the molecules going in, going out, etc. But that number can be negligible with respect to this number currently, as of today. I'm not talking about what's going to happen billions and trillions of years after our discussion. Okay, eventually the sun will also fade one day, but we are very far from that epoch. So we can confidently say that this number is, at least this exponent, is not going to change much in the foreseeable future, and even beyond that for the next few generations. Okay, so this is considered to be the standard for mass. In fact, not just the sun's mass, okay, we have one more standard called as the mass of the Jupiter, and that number, it turns out, is approximately 1.89 into 10 to the power 27 kilograms. Okay, so if you think about it, what is the heaviest planet in our solar system? What is the heaviest planet in our solar system? I'll leave that to you as a homework, okay? You can figure out. But the key idea is that your Jupiter, right, is roughly, like 10 to the power 3 times, the exact number is 1048, okay? 1048 times lighter than the sun, okay? What about the mass of the Earth itself? Just know it as a fact, okay? ME, as they call it, is something like 10 to the power 24 kilograms. The exact number is going to be something like 5.97. Okay, so this is like 5.97 times 10 to the power 24 kilograms. So why are these used as references? For comparing the masses of stars, we use the mass of the sun, that is m naught. While comparing, various other possible planets in other galaxies, okay, what are called as exoplanets normally, to exoplanets, which are planets, that are found in other galaxies beyond our solar system, okay? Not just other galaxies, but also in the Milky Way beyond the solar system. We call them exoplanets. Okay, so the mass of Jupiter is used, and because we live on Earth, right? The mass of Earth is also used sometimes in the context of astronomy and astrophysics. So please be getting to know this detail. Okay, so we next move on to the astronomical unit of length. This gets a bit more interesting than mass and time. I'll tell you why. So astronomical, I'll just call it like AU, okay, astronomical unit for length. Now 1 AU, okay, that is like 1 astronomical unit for length, is currently, okay, exactly defined to be, I mean, this is just a fact, no specific concept here. There's something, I'll tell you what it is. It's like 149,597,870 meters. Now, can you guess what this distance may be? It is some distance, right? Why choose this specific distance? Why not, 19862000199319905281? Why this specific number? It kind of should have some astronomical significance, right? Just intuitively speaking. What's your guess? Well, it could be that this number turns out to be some measure of the Earth and Sun distance. Okay. Now, of course, you can immediately ask me, well, the Earth is not, orbiting the Sun in a spherical way. It's ellipsoid. So therefore, the distance from all directions is not going to be a constant. So that's why I said it is some measure. I'm not saying that this is an exact number, but currently this is the number which is being used as like 1 AU. Okay. So this is 1 AU. What other units of length do you know from high school? Whenever we talk about distance between stars, what other numbers do we know? Well, we've always been speaking about light years, right? 1 light year. Although it is not the standard astronomical unit for length, this light year concept is very widely used, and that's why I'm giving you this number. What is its value? It's 9.461 into 10 to the power, I'll just verify, 12 kilometers. So you can look up the definition of a light year, okay? I'll actually address this in a subsequent question, but for now, because we have to proceed further, okay? So 1 light year is this distance. It is, of course, significantly larger than the astronomical unit of length itself. And the common misconception is that a light year does not correspond to dimensions of time, okay? Because you have like seconds, minutes, hours, days, months, year, okay? So it's not a dimension of time, it is rather a dimension of distance, okay? Now, there is actually one more unit associated with the astronomical unit for length. It is 1 parsec. When measuring the distance between stars, you will frequently be encountering this unit also. 1 parsec, it turns out, is approximately 3.26 light years. Okay. So this parsec concept, is slightly interesting. I will just, before going to the next ideas, I will just take you through this concept alone. We kind of know what an AU is, correct? Okay, and AU is roughly the distance between the Sun and the Earth. So let's say, like this is some point on Sun and some point on Earth, and this is 1 astronomical unit. So the parsec is actually very well defined, okay? It is actually defined as, let's say that there is some point in the star, in some star, okay? This is the Sun and this is some other star, okay? Some other star. So if you consider this distance, okay, right? If you consider the 0 degree distance between the Sun and the star, okay, right? And if you consider this angle to be 1 degrees, measured in unit of arcsec, okay, second inverse, that is okay, right? Yeah. So if this is the, I mean, I cannot draw it properly, okay, because see, if I'm considering a triangle, right, this is 90 degrees. In Euclidean geometry, this is 90 plus 1, 91, and so this should be 89. This is not what it is going to be looking like. This distance, when this angle happens to be 1 degree, is what is defined as 1 parsec. Okay. So you can use your trigonometry knowledge, right? Based on that, you can easily say that your tan 1 degrees, okay, in this unit, okay, right? That is going to be your 1 AU by 1 parsec. And after, using all the conversions that you keep doing, you will eventually get to this number, that 1 parsec is 3.26 light years. Okay, so this is the historical reason for why the parsec came into our vocabulary. All right, so this is an informal introduction to the various units that are used in the astronomical system. Are we clear? So the last question was factual. The next question will also be partly factual and partly based on chemistry, okay? So I'll delete this part and I'll go on to the next question now. Before going, I want to emphasize that we've now looked into the astronomical units of mass, length, and time, which is extremely useful when describing events such as how a planet is formed, how long it's been since it's formed, what is the distance between the stars, and etc. And in the coming days to follow, where we shall be discussing how experimentally molecules were detected in space, etc. In subsequent lectures, we shall be using some of these units, and that's why I'm introducing them to you in this tutorial itself. Okay, so the next question that we shall be talking about is as follows. This is question. Well, let's continue with the same old system from the next previous lecture. This will be question 5. This is about the magnitudes of bond energies when an electron is broken versus the magnitude of energies involved in Big Bang nucleosynthesis. Okay, so what is the magnitude of energies involved in a chemical bond and compare it with the magnitude of energies involved in nucleosynthesis. So if you find it difficult with my handwriting, this is a chemical bond and this is nucleosynthesis. And I just want to compare the magnitude of the energies involved in these processes. Now, without actually going into the experimental details, okay, you know that what happens when I say a chemical bond is broken? A chemical bond between any two atoms. Let's consider the simple reaction. So what happens when the H2 gas dissociates to form two hydrogen atoms? The bond is getting broken, right? What bond am I talking about? I'm talking about a bond that is actually this 2-electron entity, right? This line refers to 2 electrons stabilizing these 2 nuclei overall, correct? So what's getting broken is an electron pair. So when a chemical bond is broken, I break an electron pair. So I can measure using various techniques, okay, using spectroscopy in some other molecules, not for hydrogen itself, can use a calorimeter, etc., to determine how much energy is involved in this process. So this is called as the bond energy, okay. So the bond energy, when the bond gets dissociated, right, is of the magnitude of, can someone guess? For hydrogen, based on, it's not a completely new concept. You have been studying this since high school, but I just want to reiterate it in the context of astrochemistry. What's it? It's of the order of For this specific thing, it is somewhere around 400 and, if I'm correct, 36. And what are the units? Kilocalories or kilojoules per mole? Kilojoules per mole. Okay, so this is the number for HH. All right. In fact, as far as single bonds are concerned, you have so many elements in the periodic table, right? Now, to break the HH bond is the most difficult. All other numbers, right? All other numbers require lesser energy than this. Can you guess why? Again, based on the intuition gained from various chemistry courses. What could be the reason? Well, the reason is that in all other systems, okay, on top of electron nuclear attraction, okay, right? These are just, H2 molecule is the only system which comprises of two hydrogens, okay, right? And each hydrogen has only one electron and one proton. In other words, the interelectronic repulsion, okay, the interelectronic repulsion is minimized in this problem. Whereas with all the other molecules, for example, N2, you have multiple electrons. So on top of the electron nuclear attraction alone, you'll also be encountering some electron-electron repulsion. What does that do? That ensures that this amount, some amount of energy required to break the bond is actually much lesser because there is already some instability present. I hope you understood it. I'm not going to write it down. I'll just give it to you as a homework. Okay, I'll give it to you as a quick homework to understand why HH bond energy, HH single bond energy is highest with respect to other diatomics. Okay, are we all good? Yeah. The answer is simple. Again, it's the electron-electron repulsion, which is absent in hydrogen atom. Okay, now I will just sum up, giving you some important numbers based on there are some important chemical bonds, right, in chemistry. Now, when a chemical reaction is happening, it is this bond that is getting broken. So it's useful to understand some fundamental values. For example, like you take, for example, C single bond C. The value is going to be approximately 346 kilojoules per mole. Okay, of course, there will be minor variations, depends on carbon has a valency of 4. So it depends on what the functional groups are, but the magnitude will not change too much. Okay, this is for CC. And what about for, let's say, for example, let us take the example of OO. It's only 146 kilojoules per mole. Okay, and what about for NN? In fact, when considering in hydrogen, you only have the possibility of a single bond. But in molecules such as carbon, oxygen, you also have the possibility of a double bond and a triple bond also, right? So we'll come to that. We'll first discuss the single bond energies and then go to the double bond energies. Okay. What about, like, say, something like NN? A priori, between OO and NN, would you expect the magnitude to be too high or too small or almost the same between OO and NN? The magnitude of the bond energy. What would be the concept that you would base your answer on? It's based on similar electronegativity ideas, correct? So for OO, right? For OO, the atoms that the molecule gets broken into are oxygen. Here it's going to be nitrogen. And between oxygen and nitrogen, are they too different in terms of electronegativities? Not much, right? So you would expect the value to be closer. It turns out that it is 163 kilojoules per mole for NN. Okay. So, and of course, this can continue, for the halogens, etc., etc. And a good homework for you would be look up various key single bond energies. Hey, I must also tell you one more thing. every time, I talk about some energy here, right? They're always dependent on the temperature and the pressure. Okay, huh? Right now, because this is not a discussion on thermodynamics, I don't tell you, what temperature and pressure I'm talking about. Typically, these values are all at 1 atmosphere. There's also some temperature dependence, okay? But for our present discussion, we don't care about them. When we discuss thermodynamics in the context of astrochemistry, these points might become more relevant. Okay, please note that. Okay, so I will delete the question and I will give you some more relevant values. In fact, one more single bond energy that is important is actually SiO. The magnitude of SiO single bond is approximately 450 kilojoules per mole. Why is SiO relevant? Because, can you guess why? In the asteroids, recall, right? When we were discussing about asteroids and comets, in the asteroids, a lot of molecular accretion happens. So all the molecules come together, and predominantly it's the inorganic silicates which hold them together. And because of the propensity for the silicon to form multiple single oxygen SiO bonds, we have an extended structure, and there's a huge amount of energy to be gained for the multiple SiO bonds. Okay, so that's the relevance. That is the relevance of the SiO bond energy in particular. Okay. Now, just for comparison purpose, let us look at some double and triple bond values also. For example, I'll just give you two quick examples with nitrogen and oxygen. For example, the N double bond N. This is the energy to make an N single bond N. Okay, but we're talking about the energy to make an N double bond N. Okay, and that is going to be around 418 kilojoules per mole. And what about N triple bond N? What would you expect? You would expect the bond energy to be more or less. Well, there is another bond to be broken, right? So therefore, you would expect this magnitude to be higher. And it turns out to be 945 kilojoules per mole. This, in fact, is one of the strongest bond, considering all the electrons together, okay? Notice that we're not comparing, single bonds, okay? So this question, this 436 kilojoules per mole, and this being the highest for diatomics, is for the single bonds. Okay, right? When considering, like multiple bonds, the N2 bond is one of the toughest bonds to break, N triple bond N. Please make note of this. Okay, so this is for nitrogen. And for oxygen, what's going to be the value? For oxygen, it turns out to be something like 498 kilojoules per mole. Okay, are we all clear? Are we clear with the trend also? So for an O single bond O, it's much easier to make an O single bond O, but whereas an O double bond O, it becomes much more difficult. Note a subtlety. The subtlety is that here we have N triple bond N, but there is no O triple bond O. Why is that? The valence of oxygen can never be 3, right? These are simple facts, but always, remember the simple details. Whenever you're studying something new, always recollect the older details and make sure that they are consistent and compatible with the newer idea that is being presented to you. Okay, so that's why we have N triple bond N and N double bond N, but only O double bond O. So the key things to remember from this whole discussion on bond energies is that as far as single bond energies are concerned, HH has the largest one for the diatomics. It's only for single bonds. Okay, that is due to electronic repulsion. Now, the other molecules, the other diatomics, and the molecules, you can cleave the single bonds therein also, and the magnitudes of energies are given. And in general, to break a double bond, it requires more energy, and to break a triple bond, it requires even more energy. So these are the takeaways. All right, let's now look into how much energy is involved. Okay, right? When in nuclear fission or nuclear fusion, right? Look at the magnitudes of the energies involved here. These are all of the order of what? Kilojoules per mole, kilojoules per mole, kilojoules per mole, correct? What about like nuclear binding energies? Any guesses? Just, can you compare the scale? Would you expect it to be higher or lower in the first place? It would be very high, right? It would be very high to begin with, correct? Yeah. And what is the order? Without going into further details, the nuclear binding energies are of the order of mega electron volt. Notice that this is the electron volt is a different system. Okay, and mega refers to 10 to the power 6, and 1 electron volt is roughly 96.5 kilojoules per mole. So what is the magnitude of difference we're talking about, right? So it is this times. Okay, so we're talking about 96.5 times 10 to the power 6. So effectively we're talking about 9 times, 9 times 10 to the power 1. Okay, so overall there's a difference of 10 to the power 8 when you consider, right, between a kilojoule and an electron and a mega electron volt. Okay, now if you consider these magnitudes, you can see how much more difficult it is to break the or form a new nucleus. Are we clear? Okay, so to give you the measure of nuclear binding energies just with 2 samples for 12 carbon. By the way, the nuclear binding energy is vaguely defined as the net energy, okay, required to form the neutron and proton system. There are, like, let's say X neutron and Y protons involved. To form the X plus Y the nucleus containing X plus Y particles, that is what is called as the nuclear binding energy. Okay, so the nuclear binding energy of 12C carbon is going to be approximately 92 mega electron volt. So you can do the conversion here, right? So you get the measure of how different nucleosynthesis is with respect to what happens when you break a routine chemical bond. And similarly for 16 oxygen. For 16 oxygen, it's approximately 127 mega electron volt. Okay, so please take care of these numbers. Now, based on the different magnitudes of these numbers, this in kilojoules per mole versus this in mega electron volt, okay, right? You get an idea. Recall approximately in the last tutorial or the one before that, what was I telling you? I was telling you that when we were discussing nucleosynthesis, for example, the formation of deuterium 2H, the 2H isotope, right, from a proton and a neutron, I told that the electrons are not involved at all. The electrons come into the picture much later. This energy separation, the separation of energy of like 498 kilojoules per mole versus the same number multiplied by 10 to the power 6 and 96.5, right? That tells you the scale of energy separation, tells you that this can be a valid hypothesis, right? This can be a valid activity. It is that, first of all, nuclei can form involving these huge amounts of energies. And once the nuclei are formed, then of course the electrons can always be added because the amount of energies involved are much lesser. Are we good, right? Yeah. So on that note, I'll stop. And in this tutorial, we looked into majorly only 2 questions, but we discussed a lot of details. Okay. The first question was concerning the astronomical unit system. We discussed the astronomical unit of mass and length. We saw what a light year and how we can derive what a parsec meant. And after that, I gave you the list of chemical bond energies and compared that with nuclear binding energies. The key takeaway from the chemical bond energies is that for the single bond energies, hydrogen-hydrogen bond energy is the maximum number, and then for the multiple bond, for species containing the various multiple bonds, the N triple bond N is one of the strongest bonds. It's very difficult to break it. Okay, we saw that, and we also discussed how the formation of a double bond and triple bond makes it difficult to break a bond, makes it more difficult to break a bond. But overall, nothing comes even nearly close in comparison to the magnitude of nuclear binding energies. Okay, so on that note, I end today's session. And with this, like our tutorials are over, and I'll discuss in lecture 15 about the next idea. Thank you so much. You all have a good day.